Doc, Chris MacMinn, yet another former Yale postdoc. Just had to throw it out there.
Can everybody here who's a Yale postdoc please raise their
hand? Yeah. All right, carry the microphone.
Thanks. Well, I just wanted to thank the, is this working? I can't. Yeah, okay, good. I just want to thank the organizers for having me. So this is not really my usual crowd. I normally work in porous media and fluid flows in the subsurface, but much shallower and much stiffer rocks. And so as a result, a lot of the stuff that I've been hearing about over the past few days has been kind of new to me, and so I thought I would tell you about some of the things that I do, which are related but a little bit different. So I'm going to talk about large deformations in soft porous materials, and I ambitiously included a couple of things here, so squishing, swelling, and yielding, which are three ways that you can get large deformations in porous materials. I'm going to focus on swelling in the second part of the talk, and in the first part of the talk I'm going to talk about large deformations in general, and then squishing and yielding we'll have to save for another day. But Victoria did a very nice job talking about plasticity and viscoplasticity yesterday, so hopefully that is now covered. So just a quick word of introduction. So I do a whole bunch of things related to flow, transport, and deformation in porous materials. So we use experiments, mathematical modeling, and simulations, so a little bit of everything. And these are just some pretty pictures from various experiments that I'm not going to talk about today. And so, as I said, primarily for geophysical applications, so flows in the subsurface, but also a little bit for biophysical applications, so flows in tissues and things which are also soft and porous and whatnot. So the first thing that I wanted to talk about was a general framework for large deformations in porous materials. And the first thing that I should say about that is that this is certainly not new. So this is a review of things that have been known for a while and that are widely used in biomechanics in particular. But I'd like to frame it in my own way and hopefully connect it a little bit for you with the sort of things that you all usually do. So this is work that started while I was a postdoc at Yale with John Wetlaufer and Eric Dufresne, and has continued since I came to Oxford. So the first thing that I wanted to show you is a slide that I show in almost every talk that I give because I really like it. And so it's not super important in this context, but this is a really nice, I think, illustration of exactly why poromechanical deformations are so interesting. So this is a kitchen sponge. It's a cylindrical core of material, and it's oriented vertically, so you're looking at it from the side. And it has these tick marks on it that these researchers have drawn with a marker. So on the left, the sponge is undeformed, and it's sitting on top of a rigid but permeable mesh. In the middle, what they do is they press on this material with an applied load. And so what happens is that the tick marks get closer together, but they're uniformly spaced. So this is sort of traditional uniaxial deformation in an elastic material. So the stress and strain are uniform throughout the material, and everything is sort of boring and simple. But on the right, what they're doing instead is they've now removed the load, and they're driving a fluid flow through the material from top to bottom. So the fluid comes in the material at the top, flows through the material, and leaves at the bottom. And what you see is that the tick marks, again, are getting closer together, but they're now no longer uniformly spaced. And so this is, I think, a really nice illustration of the fact that the fluid is applying some sort of bulk force to the solid, and this leads to non-trivial deformations. And so that's the sort of thing that, of course, we're all interested in. And I think this is just a nice picture summary of exactly that concept. So another word of motivation, and also because the next probably 30 slides after this are going to be mainly math, so I thought it would be nice to show a pretty movie first. So this is another sort of motivating thing for what I want to talk about. This is a little sphere of what's called hydrogel. So hydrogel in this context is it's a polymer gel. So a polymer gel is a cross-linked network of polymers with an interstitial fluid. So it's a lot like the sponge that I showed you in the previous picture, except that instead of fibers, we have polymers. So the fibers of the material are essentially molecular scale, and between them there's fluid. There's actually a lot of fluid in this case. So one interesting thing about this material is that it's more than 99% water by mass. And so there's very little solid, but still it behaves like a highly deformable, highly elastic solid. So I'm going to talk in the second part of the presentation about one interesting thing about this material. So now math.
Is it contained within? Is there something around the outside?
No, there isn't. Yeah, and so I'll talk more about that. But no, it's exactly like a sponge in the sense that it's a bulk material with a pore space full of fluid, but there's no shell or anything on the outside.
Is it diperfuran?
This is polyacrylamide. I think it's more or less the same idea. Yeah. So it is. So I think, as Majid mentioned the other day, so they put these super absorbent polymers in diapers, which swell as they soak up large amounts of water, and they're convenient because a small amount of solid can absorb many, many times its own weight in water. So that's why they're great in diapers. And this is one of the materials that they use in diapers, precisely because in this case it's non-toxic and non-reactive, and so it's very safe.
And one difference with the sponge is that here the fluid or the liquid doesn't leave the
Yes,
sponge.
yeah,
Push up.
absolutely. So that's also something that I'll talk about later in the talk. Yeah, I completely agree.
And roughly, what's the porosity of this?
It's very close to 1. So 0.99 something, but I don't remember off the top of my head. Yeah.
In that shape, that's surface tension, or is it actually a bead?
It's actually, so it's a sphere. Yeah, it's actually a bead. So it's solid, although most of it is water. But yeah, it's a bulk material. So if you slice it in half, what you see is more of the same all the way through.
Okay, but I mean, if you slice that in half, you'd have 2 hemispheres.
Yeah, that's
Okay,
right.
fine.
Yeah. Yes, absolutely. Okay. So, so this is my sort of cartoon illustration of poromechanics, and this is also by way of introducing you to the notation that I'm going to use. So what we're interested in doing is coupling together a bunch of things. So there's fluid flow, fluid pressure, effective stress, which I'm going to talk about in a bit, and that's one of the main differences with the way that you like to think about things, and deformation. And so my notation is going to be V for velocity, U for displacement, and then a subscript F for what the fluid is doing, and a subscript S for what the solid is doing. And again, just to let you know, so this is all very well known, and there's a book, if you're interested, Poromechanics by Olivier Cusi, which is, again, very mathy, but I think is a nice introduction if you're into these sort of things. And so the links in this coupling are essentially the equations that we need to develop. And so the thing that links the kinematics, the deformation of the fluid flow is, of course, kinematics. The thing that links the fluid flow to the pressure is Darcy's law. The thing that links the effective stress to the pressure is mechanical equilibrium, combined with this concept of Terzaghi's effective stress in the first place. And the thing that links the effective stress to the deformation is then some sort of constitutive law for the solid. And so we need one more link, which makes my circle a little bit awkward, which is that the deformation is also related to Darcy's law via the solid velocity and the permeability, which is a function of the deformation. But we'll come back to that. So in terms of kinematics, I'm going to go through each of these little branches in the circle, and I'll try not to dwell too much. But please interrupt me with questions if anything is unclear or confusing, because my terminology will probably be slightly different. So hopefully this is non-controversial. So the idea is that what we have is a two-phase mixture. So I'm going to focus on a single solid with a single fluid in the pore space. And this is a continuum in which each point contains a volume fraction of fluid and a volume fraction of solid. So the volume fraction of fluid is the porosity, or the fluid fraction, or the void fraction, or whatever you like to call it. And the volume fraction of solid is the solid fraction. And these two things have to add to 1, because these two materials together are space-filling. So the core assumptions that I'm going to make throughout the rest of the talk, and I'm probably going to forget to mention them again, so just to point them out very clearly now. The fluid, I'm going to assume that the fluid and solid phases are individually incompressible, meaning that their individual densities don't change, they just rearrange with each other, which I think is more or less the same as what you all often do. And that the porosity is initially uniform. And so it's not completely obvious why that's an important assumption, but it has to do with large deformations, and it's a little bit subtle. I'm not going to go into the details now, but I'm happy to talk about it later. But just keep those two things in mind.
Just before you get too deep into it, are you trying to develop a model for a single one of these spheres, or for a porous medium made up out of these spheres, where the spheres are the solid?
So at the moment, I'm going to talk about a model for a porous continuum that's deformable. And so this could be a single one of these spheres, and I'll apply it to a single one of these spheres in the second half of the talk. But it could also be a packing of these spheres, which behaves also like a macroscopic porous continuum. Does that answer your question?
But when you squeeze one of these spheres,
Yep.
does water come out of it?
So this is a subtle point. I think it's best if we save that for the second half. So I'm going to talk more about how the spheres work later. But it's a good question. Was there something?
So fluid and solid is independently incompressible, but
Yes.
it tells they can be compressed.
So if you have a unit volume containing fluid and solid, you cannot change the volume of that volume. All you can do is rearrange fluid and solid within that volume. So you can change the porosity, but in order to do that, you have to push fluid somewhere else and bring solid from somewhere else. for example. Okay.
Your solid is presumably going to be both an elastic and perhaps also a viscoelastic solid.
We'll come to that too.
So that's why you're bothered about the uniform porosity.
The assumption,
Yes, exactly, yes.
the assumption of uniform initial porosity
Yeah.
makes it sound like you're only going to be able to describe the initial deformation. If you want to go to large deformations, it seems like you need to be able to start from a general initial condition.
So one of the funny things about large deformations actually is that you almost always need to reference back to a relaxed initial state. So you always need to have an initial state where the stress is 0, and that's what the displacements measure everything relative to. So that initial state can be homogeneous, and then you can do whatever you want after that. And so you can have intermediate states that are not uniform and that are not stress-free, but they're relative to a stress-free initial state. And I'm assuming that that initial state is uniform. Is that? So when you talk about large deformations, one thing you have to immediately say something about is reference frames. And so we can choose an Eulerian reference frame or a spatial reference frame, which is one that's fixed in space. And this is the way people who do fluid mechanics, and I think this community more or less always do things. So this means that your independent variables are some fixed position in space and time. And it means that the reference configuration of your material, of your solid, say, so this is the relaxed initial state, is described by a function of space and time. So at any point in space, I have a function that tells me where that piece of material that's currently at that point came from. And then we have a displacement field which measures precisely how far that piece of material traveled from where it came from. So it's just the difference between the current position of the material and the one where that piece of material started. So the other option, which is very, I'd say universal in solid mechanics, is the choice of a Lagrangian or a material frame. And this means that your coordinate system is anchored to your solid. So as a result, your primary variables are actually the initial position of material points and time. And your current configuration is something that you need to know for every reference position. And the displacement field is defined in the same way, but now the current configuration is the one that's varying, and the reference configuration is just the fixed spatial coordinate. So I'm going to work in the Eulerian frame, which I think, personally, coming from a fluids background, is a lot easier to understand. There are times when doing computations that this is not so convenient, particularly when you have a complicated object that's deforming with moving boundaries and whatnot, which is precisely why solid mechanics people prefer the Lagrangian framework. But I think for these purposes, it's a lot easier to understand how things are working in the Eulerian frame. So especially for anybody coming from solid mechanics, some of the things that I'm going to show you in a moment are a little funny looking, and it's precisely because of this. So they look different in an Eulerian frame than in a Lagrangian one. So with all that said, we can write down some basic equations of kinematics. So the first two should be obvious. I think they are one of these boards. They were at some point, but we've seen them quite a lot. So this is just conservation of mass or continuity with no melting or dissolving or phase change or anything like that. And the third one is maybe a little bit unusual. So this is simply the fact that the solid velocity is the material derivative of the solid displacement. So when you're in the small deformation limit, you can just take a time derivative of the displacement to get the velocity. But for large deformations, you have to be more careful, and we need to use a material derivative. So this sort of thing is, I think, not unfamiliar to you. And additionally, we need a bit more about the changing geometry. So we have the fact that the two void fractions, the two volume fractions add to 1.
So the US is displacement, yeah?
Yes. And we have to introduce this quantity called the deformation gradient tensor. So this is this capital F. And I'm defining it here via its inverse, because in an Eulerian frame, this is a little bit more convenient. The idea is that this measures how much your configuration has changed from where you started. So it's a tensor that's constructed by essentially taking the gradient of the displacement field. And then a very important quantity, or property of the deformation gradient tensor, is the Jacobian determinant, which is just the determinant of the deformation gradient tensor. So that's this thing J. So J is the determinant of F, and J precisely measures how the volume at a point has changed over time as a result of the deformation. And as a result of that, J is directly related to the porosity. So if I know my initial porosity and I know my deformation field, then if I calculate the Jacobian determinant of that deformation field at a point, that has to tell me how the porosity at that point has changed. And this is the statement that becomes a lot more complicated if your initial porosity is not uniform.
That is assuming that rho s is constant.
Yes, yes, incompressible constituents. Yeah, absolutely.
How is that different from the divergence of displacement?
We'll come back to that. Yeah. So the short answer is that this is the large deformation version of the divergence of the displacement field. So for small strains, it is the divergence of the displacement field. But there's nonlinearities here that are not there.
Is it possible to rearrange that third equation so that it's explicit in velocity of the solid?
Yes. Yes, it is. So I think it looks like the solid velocity equals the time derivative of the solid displacement times the deformation gradient tensor, or the transpose of the deformation gradient tensor, or the inverse. I can't remember, but one of those. So yes is the short answer.
Is it fair to say that this is a constrained form of two interpenetrating continua, for which there is a large literature?
I think so, yes, I would say. So we will diverge from that on the next slide, I think. But yes, so for now, this is just the continuum mechanics of two interpenetrating continua, exactly. Okay? So that's kinematics. So next we have Darcy's law. So Darcy's law, again, is meant to relate the fluid flow to the pressure. And this part, again, I hope should be a bit non-controversial. So Darcy's law looks as you're used to seeing it. So we have a porosity times the difference in velocities between the fluid and the solid, and this is driven by gradients in pressure. And the permeability is a function of, let's say, the porosity. So one example that people often like to use, at least in the porous media community, is what's called the Kozany-Kármán relation, which is up here. It's just one particular functional form of the permeability as a function of porosity. But it has two nice features which actually tend to help keeping your pore mechanics well posed. And those are the fact that the permeability goes to zero as the porosity goes to zero, which helps prevent the deformation from driving negative porosities, which are things you obviously don't want. And the permeability diverges as the porosity goes to 1, which helps prevent your deformation from driving porosities above 1, which is also something that you don't want. Because in principle, nothing about the equations that I just showed you prevents that.
P is the pressure in the fluid.
Yes. Yes, yeah, that's an important point. So P is the pressure in the fluid. I'm not going to talk about a pressure in the solid, and I'll explain why in a moment. So just two notes. Disadvantages of assuming that the permeability is a function of the porosity are that we're assuming that this permeability field is isotropic, and we're assuming that the deformation preserves isotropy, because the porosity doesn't capture anything about distortions of the solid skeleton. It only captures changes in volume. So that means that if your deformation is such that you should get an anisotropic permeability field as a result, you can't represent it like this. Additionally, well, actually, this is more or less what I just said. So it reflects volumetric deformations only. So shear deformations have no influence on the permeability if your permeability is only a function of porosity. So just a note. Okay, so now we need to say something about mechanical equilibrium. And for this, the way this is commonly done in the porous media community is through what's called Terzaghis effective stress. So I'm going to try to explain to you why we do it this way. So here's a bunch of quantities that I think we've to some extent heard about already. So the fluid stress tensor is the force per unit area of fluid supported by the fluid. And we assume that that's compressive and isotropic and given by the fluid pressure. The solid stress tensor is the force per unit area of solid supported by the solid. And then the total stress, or the mean stress, or whatever you'd like to call it, is just the volume-weighted sum of these two things. And mechanical equilibrium requires that the divergence of the total stress be balanced by gravity or whatever other body forces you may have acting if we're neglecting inertia, which I definitely will do. So is that okay so far? So then what you like to do, at least as far as I can tell, is define a pressure in the solid phase and maybe multiple pressures in the solid phase, and then think about how these different pressures cause different physics. So what people in the porous media community like to do is define what we call the effective stress, or Terzaghis effective stress. And so the motivation for this is that it's nice to think about a quantity which is directly related to the deformation. And if your solid constituent is incompressible, then the fluid pressure itself doesn't deform the solid. So the idea is that if I have a handful of sand, it doesn't matter, the mechanics of this handful of sand don't change if it's at the bottom of a bathtub or a swimming pool or the ocean. The absolute value of the fluid pressure doesn't deform the sand if the sand grains are incompressible. So what I care about are the other stresses in the sand. And so the effective stress is a way of just removing the fluid pressure from the stress in the solid. So I take my solid stress, I remove the fluid pressure, which means adding the fluid pressure because it's a negative quantity, it's compressive. And then I multiply by 1 minus the porosity to take this from being a quantity that's per unit area of solid to a quantity that's per unit total area. So the idea is that the effective stress is the component of the stress in the solid that's related to the deformation of the solid. So there's also an isotropic compression within the solid skeleton because of the fluid pressure, and this doesn't do anything with regard to deformation if your solid constituent is incompressible. So if I define my effective stress in this way, so far this is just a definition, we haven't actually assumed anything, then I can rewrite the equations above like this. So my total stress is then simply my effective stress minus the pressure. The divergence of the total stress becomes the divergence of the effective stress, and I can put a pressure gradient on the right-hand side. And then I need a constitutive law. And so there's two constitutive assumptions here. One is, how is the effective stress related to the deformation of the solid? And the second is that the effective stress is the component of the stress that's related to the deformation of the solid. So I don't need to worry about the fluid pressure when I think about the deformation of the solid.
Comment.
Yeah.
The equations that Dan wrote down originally are actually consistent with this because he chooses the P in his definition of stress to be fluid pressure. So they are
Perfect.
Yeah.
Oh, that's very good.
If I can quickly add to this, and if you would split the effective stress into deviatoric and the volumetric part,
Yes.
the volumetric part would be exactly what we call compaction pressure. So that's another way that it
that's
exactly relates
also
to what we
absolutely
do.
true.
I think we're consistent.
Good. Well, I mean, I guess the physics are the same, right? So that's comforting. Any other questions or comments?
Equilibrium which would connect my velocity of fluid with total stresses according to what's written.
The velocity of fluid. So we'll come back to that. Okay, so then we need a constitutive law for the solid. And here you can do a lot of different things depending on what your solid is doing. So of course you can have an elasticity law, in which case the stress in the solid is related to the displacements in the solid, or really the gradients of the displacements in the solid. Or you can have an elastoplastic law, or a viscoelastic law, or a viscoelastoplastic law. So Victoria covered more or less all of those bases yesterday. Today I'm going to focus on elasticity only. So what this means is that the effective stress is a function of the strain, and the strain is then a function of the deformation, meaning the gradients of the displacement field. And the reason that this is a headache compared to, say, a viscous rheology is because then you need a reference configuration, and you always need to know how far you are from your reference configuration. And that calculation and the geometry associated with that becomes a bit of a mess when the deformations are large. Okay, so one example would be linear elasticity. So if your deformations are small, then linear elasticity, it seems to be a very good way to do things. Linear elasticity looks like this at the top. So the effective stress is a function of this small strain tensor, which is itself related to gradients and displacement in a very familiar way. And I'm using two material properties, which are the P-wave modulus and Lemay's first parameter, which I'm using a capital lambda because these things called stretches will come up later, for which we use a little lambda. And the key thing is that these are drained material properties. So this is terminology from soil and rock mechanics. What this means is that these are material properties of the solid skeleton only. So if I have a porous solid and I take out all the fluid and deform it, these are the mechanical properties that I care about. Or in other words, if I take the porosity to 0, so I have just an elastic solid, then these equations should still work. So you do not need a fluid in order for these properties to be relevant to what the solid is doing.
Are you implying that the strain should be defined differently if it is nonlinear elasticity?
Yes. Yes, although I have to say, so when I started doing these things, I initially felt that strain was fairly clear because strain is calculated from displacement, which is all kinematics, and that the relationship between stress and strain was a bit fuzzy because this is where constitutive modeling comes in. But actually, I think it's better to think of stress as being the thing that's very clearly defined because it comes from force balance, and strain is where things get a little bit fuzzy because strain has to do with how you relate stress to strain energy, and there's various definitions, yeah. So strain is a funny thing. This is the small strain tensor. I'm going to show you another one in a moment. Anything else about this before I? Okay, so this is a very simple large strain representation. So this is called Henke elasticity. And the first equation looks almost exactly the same as linear elasticity, except that I've now called the strain tensor H, which is the Henke strain tensor. And I put a J on the left-hand side. So this reflects the fact that the volume of material elements is changing with a deformation, which changes the way they respond to strain. And so the Henke strain tensor is not the same as the small strain tensor. It is logarithmic in particular, which apparently reflects better what real materials do under, say, moderate deformation, so tens of % of strain, whereas linear elasticity is really only good in most materials up to fractions of a % of strain. So Henke elasticity is nice because it's basically the simplest large deformation elastic law that captures the full deformation, the full nonlinearity of the changing geometry of the body. And it also takes the same two constitutive parameters as linear elasticity, and it simplifies to linear elasticity for small strain. So if you do a Taylor expansion of this for the gradients of displacement being small, then you get back to exactly what I showed you a moment ago, which is a nice feature, and not all large deformation models will do this. I think that's everything I wanted to say about that. So this is just an example. I'm not actually going to use it in anything here, but just to give you a sense for where things start to become different. And this is, again, a very simple one. So normally they are rather beastly, actually. Mark, did you have a?
Is some potential?
So H is the Henke strain.
Strain.
The strain, yes, which is just some function of gradients of displacement. Anything else?
J is just the determinant.
J is the determinant of the deformation gradient tensor. Yeah, exactly. Okay, so this is our picture. And so if we take all of these equations that I just showed you and put them together, one way to write all of this is as follows. So at the top we have an equation for flow. So this is an evolution equation for the porosity, and it has an advective-like piece, which is the porosity being carried by a total flux, which is itself divergence-free. So that's on the second line there. And then there's a diffusive-like piece, which has to do with gradients and pressure, which are then related to the mechanics. And so the mechanics, we have that the divergence of the effective stress has to be balanced by gradients and pressure, and I left out gravity here, but it's obviously straightforward to put it in. And then we need some sort of constitutive law relating the effective stress to the deformation. And then we have the geometry, which is that the deformation gradient tensor is related to gradients and deformation, and that will pop up in this relationship. And that the determinant of the deformation gradient tensor is itself tied back to the porosity. So we have to make sure that our deformation is kinematically consistent. Okay? It's a lot of equations, I know.
Density of fluid become like porosity of fluid in a sense.
So the density of fluid is constant, I'm assuming. The porosity is the volume fraction of fluid locally. So it's at a point in my material, how much of that volume is fluid versus solid. And the porosity can change, but the density cannot.
Total porosity has to stay the same, yeah?
Yes, that's right. So if you have some sort of porous material in a box, you can't change the porosity of your box, the total porosity of what's in your box, but you can change the local values by rearranging. Yeah, exactly. Okay, so I have this picture again. Right, so linear poroelasticity is a theory that I think has been tremendously successful in hydrogeology and hydrology and petroleum engineering. And I just like to point out exactly where linear poroelasticity deviates from what I just told you. So the obvious thing is that you use linear elasticity as your constitutive law between the stress and the strain and the solid. The less obvious thing is that actually we linearize most of this picture. So linear poroelasticity will be different in all of these ways. And that's because the equations that I just showed you are not linear. And they're not linear actually primarily because of the kinematics, not so much because of the constitutive law. But of course, they can also be nonlinear in the constitutive law. So just to compare side by side, this on the left is what I showed you before. And on the right is what you get when you simplify this based on the assumption of small strain. So the nice thing is that all the equations are linear, and so this is where your divergence of displacement comes in. But I think it's important to note that when we use linear poroelasticity, which we often do, you are approximating not just the relationship between stress and strain, but actually the entire kinematics of the deformation. And that, as your strains become non-negligible, that introduces errors in all sorts of things, in particular in the dynamics. So the rate at which things happen will not be the correct rate, and that can become a problem if your deformations are not so small.
F0 means original. What means?
So this is, this is the initial porosity. Yes.
Any heuristics for how small is small?
Okay, so if that's something you're interested in, then more or less everything that I just told you, plus an analysis of exactly what is the difference between linear poroelasticity and a nonlinear model as a function of how big the strain is. We wrote a very long paper about this, which you can easily find on the archive if you're interested. And I'm not going to talk about the rest of that stuff now because it's to some extent sort of what you would expect. So obviously as the strain becomes non-negligible, you get errors which are second order in the strain, but there are also some interesting things to it. Okay, so that's the theory. You survived the math part. There's more math coming. So next I'd like to talk about swelling and drying of a spherical gel. So this is work that I've been doing with colleagues at Yale and also CNRS. And I should say most of the experiments that I'm going to show you I did not do. So they were mostly done by George and also 1 or 2 by Thibaut and 1 or 2 by me. So now we'll talk about this squishy bead a little bit more. So this is the movie that I showed you before. So again, a polymeric gel is a cross-linked network of polymers with an interstitial fluid, and they have a very low solid fraction. So the majority of what you're looking at is actually liquid, which then, of course, makes you wonder, why does it behave like a solid? So these things, when they're dry, they are small, obviously, and they're also hard. So a dry bead, if I were to take this and just leave it out for a couple of hours, is a small, hard ball of polymer, essentially. And when I put it in liquid, it will swell. And I'm going to show you a movie of that in a moment. And so why do they swell? So swelling is the spontaneous imbibition of additional pore fluid because there's a strong chemical affinity between the fluid and the solid. And so this leads to potentially very large volume changes, as I'm going to show you. And one important thing is that the swollen sphere is a lot softer than the dry sphere. So in addition to becoming a lot bigger, it becomes a lot softer as it swells up. So this is a not particularly good movie of the swelling of one of these beads. So this is the initial state. And what we do is we stick it in some water, and then we just make a movie of what happens. So this is what happens. So there's 2 things that I think are worth noting about this movie. So the first thing is that the bead grows by a lot. So its radius, it says this on the next slide, but I want to wait for the movie to finish. Its radius increases by a factor of almost 5, which means its volume increases by a factor of something like 100. And additionally, okay, I think that's enough. So it swells a lot. And additionally, you may have noticed that even though it starts as a sphere and finishes as a sphere, in between it's not spherical. So there's an intermediate state which is lumpy, if you like. So this is a transient poromechanical instability. So this instability leads to pattern formation on the surface of the sphere that evolves and then goes away. And so one of the things that we'd like to understand is what is going on with that. So it depends what you mean exactly. So I think
the difference between the 2 movies.
Right. So the characteristics of the pattern, say the typical wavelength or the number of lobes or whatever, are fairly reproducible. But whether they appear in the same place every time, I don't know. I would guess probably not, but it's hard to say. Is that what you were asking?
It's not traceable to imperfections in the initial bead.
It seems not to be. Yeah, not in any way that we're aware of. So it is really a mechanical instability, and I'll give you a little bit more evidence of that in a few minutes. So this is just the movie again, showing you the initial size and the final size, emphasizing the fact that it really does grow by a lot. So this is not a small deformation problem. So you cannot use linear pore elasticity for this problem. The geometry changes enormously, and so do all of the material properties. And so as a result, you really have to be careful with your large deformation stuff.
The feature is not homogeneous.
Sorry, what about?
It's not homogeneous. The porosity is not homogeneous.
During the swelling process, the porosity is not homogeneous. In the initial state, it is, and in the final state, it is. But in between, it's not.
And any information about isotropy during the process?
So, no, I guess is the short answer. We really don't know. Thinking about so I'll mention briefly a function for the permeability of the bead, and we're just going to use one that's a function of porosity, which I already told you is not always a good idea. And the reason is that it's just extremely difficult to measure. Have you looked at this at all?
No. We actually model this as one piece and don't model it distributed.
I see. Okay.
Because we model a bed of them.
Yeah. Okay. Yeah.
Chris, can I also ask the
Yes.
initial radius or the initial circle as we see it here and the final circle don't have the same center?
Yeah, it wanders around a little bit during the swelling process. And so this is essentially because, well, partially because these lobes appear on all the sides, including the side that it's sitting on, and so it will sort of roll around a little. And also because in order to swell one of these beads, you put it in water. And in the final state, it's 99-point-something% water, which means it's almost perfectly neutrally buoyant. And so it doesn't take much for it to sort of drift around in the cup of water it's sitting in.
What if you put in a layer of water that there wasn't enough water to...
Yeah.
It didn't...
Yeah, these are good questions. I'm not sure I have good answers, but it would soak up as much as it feels like soaking up. And how much it feels like soaking up is something that we'll talk about in a moment, at least to some extent.
Do you think that instability can be explained wholly satisfactorily by the model you've got? Or do you need anything to describe the way that the spherical porosity as you envisaged it initially is in fact distorted? Therefore it becomes, there's a non-isotropy in the system.
Right. So I suspect that the leading order effects can be described by the model that we have. But that's not to say that the anisotropy is not important. One reason that I think the model that we have should work relatively well is that the flow is very strongly radial. And so even if the permeability in the azimuthal direction is quite different from the one in the radial direction, I think that doesn't matter so much. But it's a good question. So okay, so I'm going to show you one more movie, which is now not this same bead, but one of these same beads taken out of the water and left on the counter for a couple of hours. So this is now the drying process. So here's the bead. This movie is slightly more pretty. And so you might naively expect that the drying process looks just like the swelling process in reverse, but in fact, it doesn't. So when you dry one of these beads, it starts as a sphere and ends as a sphere, but in between it stays a sphere. So this transient instability that happens during the swelling process does not happen during the drying process. So this is a first hint that the mechanics of what's going on inside the bead are quite different during drying than they are during swelling. It's got a little ways to go yet.
Okay. One of your previous slides, it didn't seem to start as a sphere.
It should have done. If it didn't look like a sphere, it's either because the first frame was not exactly t=0, or it could just be that it looked a little bit funny. Are you thinking of one of these?
No. Quite a lot back.
Okay, yeah, well, let's say it should have, yeah.
Okay.
Right, so drying is mechanically stable. So the question is, what can we try to understand about this based on the modeling that I talked about at the beginning? And so one sort of leading order thing that we might like to try to predict is just the radius versus time, and the mean radius, of course, because it's lumpy, so you have to define something. But if you do try to measure the mean radius versus time, you get a nice smooth curve, so that's swelling on the left. And then when you dry it, obviously the mean radius is very well defined, and this is again a nice smooth curve, and these curves look very different. So there's a variety of things about them that are different. One is just the shape, of course, but another one is the fact that swelling is rather fast, and you can see drying takes a lot longer. So that's a subtle point that I hopefully will have a moment to talk about at the end, but we'll see.
But your drying curve doesn't end at 1.
Yeah, that's true. So that I was hoping no one was going to mention that. So this is also a subtle point. So the issue is that the dry size of the sphere is very sensitive to things like the temperature and humidity in the room, as is the swollen size of the sphere. And so drying takes a day basically. And so if you start in the room in the morning and you let it dry out, and then you come back the next day and you look at it, it may not be quite the same as it was when you started. So in principle, it's reversible, but in practice, it's a little bit complicated. So we have to tweak our model just a little bit. And so to do that, I need to talk about chemistry just a little bit. I'm not a chemist. So there's already a theory for how gels swell, which is convenient. And the theory is based on the assumption that the free energy of the gel, so that's this thing that I'm calling W, is the superposition of two things. So there's a contribution due to stretching of the polymer molecules and a contribution due to mixing, because the polymer molecules like to be next to the water molecules. And so in order to derive some equations for how this works, we then can look at equilibrium for the gel, which says that the incremental change in the free energy is balanced by the amount of mechanical work that I do to the gel plus the amount of water that I try to stuff inside the gel, basically. So this mu is now the chemical potential. So mu was previously the viscosity of the fluid, and now it's the chemical potential. So I'm sorry, but that's just what happened. So the chemical potential is the incremental work to add another water molecule to the gel. And so for stretching, we use what's called a Gaussian chain model, which has been developed in the context of rubber elasticity. So this is basically assuming that your gel is made up of an isotropic network of polymer chains, and as you stretch them, there's some sort of entropic penalty for stretching them, and you can then calculate what the elastic energy should be as a function of that. And then the mixing comes from the theory of polymer solutions. And the idea, one way to think about it, is that when you swell one of these gels, it's the same as essentially putting something soluble into water. So putting sugar into your water, to use Majid's analogy from the other day, except that you can't have the molecules of the solute just running off into the fluid because they're attached to each other. So essentially what the gel is trying to do is to mix itself with the water, but the only way that it can do that is by sucking the water in. It can't go out into the fluid. And so when we do this, what we get is something, oh yeah, sorry. The lambda, were the lambda? Oh yeah, so lambdas are stretches. So yeah, that's important. So you can think of the lambda as a strain, essentially. It's not quite a strain. It's sort of like 1 plus a strain. So lambda equals 1 is the undeformed state, and lambda greater than 1 it means you're stretching it. Lambda less than 1 means you're squishing it. And they are lambda squared are the eigenvalues of F. But just think of it as strain. It's easier.
Subscripts are directions? Or?
The subscripts are the three, yeah, so there are 3 principal directions in this case, which will make a little more sense in a moment. But yeah, absolutely. Yeah, please point out if I don't explain my notation, because I know it changed a bit going from the previous stuff to this.
The equilibrium condition is dW equals 0, or W minimum.
So the change in the free energy has to be balanced by the work that I do. That's the idea. And so this is the free energy of any state, and then this is the work that I'm doing on the gel. So this is the mechanical work, and this is the sort of chemical work, if you like. I may be explaining it in a slightly hand-wavy way, because as I said, I'm not a chemist, but that's the rough idea.
It's not an equilibrium condition, it's just a conservation law.
So what it leads to are the constitutive equations for the gel, which is what I'm going to show you in a moment. So I don't know if that'll help or not, but maybe I should show you. So the idea is that this gives us an equation for the total stresses within the gel. So on the left is this sigma I, which are the principal components of the total stress tensor. And then this has 3 contributions. So there's a stretching contribution, which comes from this Gaussian chain model. And then there's essentially a chemistry contribution. So there's an osmotic pressure, that's this pi mix, which I'll talk about in a minute, and then the chemical potential. And so if we think about this in a poromechanical way, we can interpret these different contributions in a way that connects back with what we were just talking about. So the stretching contribution is really the effective stress in the polymer network. So that's the fraction of the stress that's being supported by the polymer chains through stretching. And then the other 2 pieces together make up what I can call the fluid pressure, or what I'm going to call the fluid pressure, whether I can or not. And so the one way to think about the fluid pressure is that there's a chemical potential, which has a mechanical component, which is the fluid pressure, and then a chemical component, which is the osmotic pressure. And Darcy flow then looks only slightly different from before, so I'm using eta for the fluid viscosity now instead of mu because of the chemical potential. And now Darcy flow is driven by gradients in chemical potential rather than by gradients just in pressure. So it's a little bit in debate whether one should use Darcy flow or diffusion or something else for transport within a gel, since this is happening at the molecular level. But in fact, it doesn't matter that much how you want to think about it, because they all end up being some sort of nonlinear function of porosity times a gradient in chemical potential. So whether you think of it as Darcy flow or as some sort of complicated diffusive mass transport, it ends up being the same, essentially.
What's the big omega again? Sorry.
So the chemical potential is the incremental work that is required to put one additional water molecule into the gel. So it's a work per unit water molecule. And the big omega is the volume of a water molecule, which is a fantastic quantity to appear in your equations. It's a very small number.
Energy per volume then.
So that converts, so mu over omega is the energy per unit volume instead of the energy per unit molecule. Yeah.
Can I call it just phi flow?
Sorry, in the linear case, it's the same as Fick's law. Yeah, so if k is constant, then this is just Fick's law for diffusion.
Diffusion equation, doesn't it relate concentration to the gradient of chemical potential and not the Darcy flow?
So there is a relationship between the concentration and the chemical potential. I'm probably not the one to explain it to you, but maybe you have a clear idea?
Relationship between concentration and chemical potential?
Yes.
Activities, ideal solution theory, or some perturbation thereof.
I'm not sure if that helped.
I'm not just sure that you can actually write diffusion equation in that way and relate gradient in chemical potential to Darcy flux.
So I think you can. There's a paper about it, which is titled something along the lines of Fick's law and Darcy's law are equivalent. Rich knows a lot more about it than I do, I think.
What was the question?
So the question was whether you can just think of Darcy's law and Fick's law as being interchangeable, both being something times a gradient in chemical potential.
From non-equilibrium linear transport theory, actually, they're the same thing, right? Like an electrical flux, a current, basically, also electricity is the same thing.
Species flux, but do you have, some chemical species gradients? And this is what Victoria is asking, not just expressing chemical potential in terms of pressure.
So the species is the relative amount of fluid versus solid, right? So the thing that's diffusing is the porosity, essentially. So this is, again, the gel is trying to mix itself with the liquid. And so it pulls in liquid, and this is what changes so the concentration and the porosity are directly related to each other in this case. I think they're linearly related to each other. Is we okay so far? Ish. Majid.
One thing is a little confusing is that when you write Darcy's law, the velocity is on the left.
Yes.
Those are macro scale quantities.
Yes.
Average over large amount of water.
Yes.
Then on the right you talk about molecular properties?
Well, so they're sort of, they are molecular, but they're at the continuum level. So it's the chemical potential at a point, and your point isn't really an ReV. So we're not modeling at the molecular level. It's still a continuum.
If you replace Boltzmann's constant with the gas constant and volume per atom with volume per mole, it's exactly the same equation, except you no longer have tiny numbers and aren't thinking about atoms.
Fair enough. Okay, so I'm gonna take another step. So this is the
pi mix. Did you explain pi mix?
I didn't. I think. Yeah, so I will. Maybe now. So pi mix is the upper right. It's hiding. So pi mix is the negative of the derivative of the free energy of mixing with respect to the Jacobian determinant, which is the same as taking the derivative with respect to the concentration. So this is now the theory that we're working with. So it's more or less exactly the same as what I showed you before, except, so in the equation at the top, instead of gradients in pressure, we have gradients in chemical potential. The second line is the same. The third line is the same, except that now we have chemical potential and an osmotic pressure instead of just a pressure. And in the third line, we need two constitutive laws. One that relates the effective stress, so the stretching in the polymers, to the deformation, so how much the polymers are stretched. And another one for the osmotic pressure, so how badly the fluid wants to be inside the solid. And this is a constitutive law. And if the chemical contributions are negligible, so if there's no osmotic pressure, I set pi mix equal to 0. This is exactly what I showed you before. So everything simplifies nicely to sort of regular poromechanics. And so now I'm going to simplify for spherical symmetry. The next slide has a lot of equations because the 3D version of this problem is rather nasty for a variety of reasons, mainly having to do with the lobes, you may have noticed. So this is the spherically symmetric version. I don't really want to dwell on it, but I just thought it would be useful to make the equations a little bit more concrete instead of being sort of abstract vector equations. And I'm also now including, this is the constitutive law again for this Gaussian chain model for stretching. And this is the constitutive law for the osmotic pressure. And this is, again, effectively from chemistry. This has been suggested for a long time as an osmotic pressure for the mixing of polymers in a solution. And it has a couple material parameters that I don't really want to get into. So there's an alpha, there's a chi, and this part's okay. But that's the idea. So geometry. So this is how the porosity is related to the displacement for spherical symmetry. And so if the deformations are small, then these two terms are not important, and we go back to something that's just the divergence in spherical symmetry. But of course, these two terms are definitely not small in this case. The Jacobian determinant is related to the product of the three stretches, which again are the eigenvalues of the deformation gradient tensor, or the square roots. And that's directly related to the porosity, where now the initial porosity is 0. So the relaxed state is one in which there is no water in the gel. And then the stretches are related to the displacements like this. So that's all the math. So now we can solve these equations. And so I'm going to show you a bunch of things. I don't want you to try to figure out what's going on with all of these plots because we don't have a lot of time and it's kind of complicated. So
you haven't given us any boundary conditions.
Yep, so they're here. So
Mentioned.
That's right, yes. So the boundary conditions are the following. Inside the gel, the chemical potential is uniform. And based on that uniform chemical potential, you can calculate everything else. And outside the gel, the chemical potential is different. So we change the chemical potential outside. And then that information will propagate into the gel, which drives either swelling or drying, depending on whether the chemical potential outside is bigger or smaller than the uniform one inside. And this is free swelling, which just means that there's no mechanical constraint at the outer boundary. So we're not pushing on the gel, we're not pulling on the gel, it's just free to do whatever it wants. So there's a lot of quantities here. So the first, upper left is porosity, upper right is displacement, and this is all dimensionless, by the way, which is why the quantities look complicated. So the middle column, the middle row, is stress. So there's the radial effective stress and the azimuthal effective stress, and then pressure and chemical potential. I'm showing you, sorry?
Is the initial condition.
So I'm showing you two states. So the lighter color is the initial condition, and the darker color is the final state. And so the final state, it's always nice to work in a problem that has a steady state where everything is finished. And so the final state is simple. It's just that it's stretched out. So you can see that we go from a porosity that's close to 0, so the gel is not exactly dry at the beginning, but it's close to dry, to a porosity that's nearly 1. The displacement is initially 0 and goes to a line. And then we have some other things that happen. So the chemical potential initially is very low, which is what happens when you put the gel in water. And then, which is what happens when the gel is sitting out of water. And then the chemical potential of water, when you put the gel in, is basically 0. And so you go to 0 uniformly inside eventually. And so I think there's only one thing that I want to highlight about what I'm going to show you next, which is the time evolution of all of these quantities. So that looks like this. And that one, well, let's say two things. So one is that it's complicated. And two is that it's non-monotonic, both in space and in time. So for example, if you think about the azimuthal effective stress, near the center of the gel, we start down here, it goes up to here, and then it comes back down to here. And so there's a lot of complicated things going on within the gel as the water content evolves. And in the interest of time, I don't think I'm going to talk more about the details. But of course, I'm happy to talk about it later. But so the macroscopic thing that we wanted to try to predict was the radius as a function of time. And so we can do that. So this is the experiment and now the model. There are two fitting parameters here. So one is the final size, which is a function of the chemistry of the gel, and it's something you measure by swelling the gel and seeing how big it gets. And two is the rate. And the reason that you need to fit the rate is, again, because measuring the permeability of these gels is very hard. So once you know the time scale and the final size, then you can fit this curve. And the shape is whatever it wants to be. So the shape matches very nicely.
Are there non-dimensional parameters that actually, when you say you fit the rate, you're fitting a bunch of things stuck together?
So the rate only goes into the time scale. So the model, we work with the model in dimensionless form. And the only non-dimensional parameters in the dimensionless form of the model control the final size. They don't control the rate. And so when you take that dimensionless solution and you want to plot it versus physical time, then you need to choose the time scale. And that's where that fitting comes in.
How far off is that, at least initial cases, from square root t?
That is a good question. It's not square root of t. I have a log version of this plot, but this is not it.
Normally
yeah.
it's a fusion problem.
Yeah, of course. Yeah, so it's not square root of t, but it's not so far.
Yeah,
so
it's got that sharp.
Yeah, exactly.
It's sort of rebounded.
The two parameters that
So
you
your
use
Fusion is
to pick
here,
on
still
it,
square root.
Yes.
final value
Yes.
and the rate at which it
And when I say the rate, I just mean so there's basically a horizontal scale that you have to choose for this plot.
But if I could choose those two parameters to help with the theory, even if I didn't understand something,
Yeah.
I could write down a
Well,
function that would presumably be pretty close to this.
well, you wouldn't necessarily get the shape. I guess that's the thing.
The richness is in the deviation of that shape from square root of t, which is hard to see on this plot.
Yeah, that's absolutely true. Yes. And of course, all the complicated stuff that happens within the gel during the evolution, which is stuff that I didn't talk about. And I'm not going to talk about because it's almost lunchtime. So then you can say some things about the transient surface patterns.
One quick question, the
Yes.
previous graph, is that the calibration you've done or is that the prediction you've done? You fitted parameters to get the curve right or
Yes.
the other?
No, you swell the gel and you measure its final size and how long it takes to get to that final size. And then you stick those two numbers into the model and then this is what you get. So the fact that the time scale agrees nicely and the final size agrees nicely should not be impressive. Those are imposed.
Scale to graph.
Yeah, essentially, exactly. But the shape is the thing that's really, I guess, indicates the model is doing something right. But I agree, there's a lot of subtlety in exactly what that shape is.
Will you show us the drawing?
I will, sort of. So, okay, so I'm going to skip ahead quickly just to get to the drying stuff. So you can say some things about the number of lobes. This is just measurements of the number of lobes as a function of time, and other people have done this as well. And the fact that you get a surface pattern during the swelling of gels is not new. So people have known this for a long time and studied it in a variety of contexts. And the reason it happens is actually kind of intuitively obvious. So when you put a gel into water, what happens is that the outer layers of the gel are exposed to water first, and they want to grow in order to bring more water in, but they're attached to the inner layers, which have a harder time getting to the water, and which are still rigid and small. And so the outer layers basically bulge on top of the inner layers, and this generates the mechanical instability. And that goes away as the water content becomes uniform within the gel. So this is sort of exactly that phenomenon in a variety of different contexts. This is another movie of swelling, which I'll show you just because it's pretty. So this is using a shadow graph. And one of the nice things about doing it this way is that you can get an idea of a little bit what's going on inside the gel during the swelling process. So you can see there's a dark core that is evolving along with the outside. And then you can measure some things. And then this is a prediction of the model that I'm not going to talk about. So I guess one thing I will say about this is that the model very clearly shows us that there is a soft shell that's in compression as the gel is evolving. So this is the mean total stress, and this is the shear stress, R on the vertical axis and T on the horizontal axis, so it's a space-time diagram. And we can see very clearly that there's this layer on the outside that's being squished as the gel is swelling, and then that fades away as the gel finishes its swelling process. And that layer is also in strong shear. So this is definitely not directly correlated with this plot of the radius of the hard core and the soft shell as a function of time, but there's something sort of suggestive there about the fact that we're getting these shapes. Okay, so now drying. Unless there's any more questions about swelling, but I think we should probably move it along. Okay, so drying. So initial states and final states. So the only difference between drying and swelling is that the initial state is now swollen and the final state is going to be dry. So I take my initial states and final states and my boundary conditions from before and I just precisely reverse them. So these plots are all showing you the same thing that you saw before. And so again, two important points. One is that it's complicated. And two, so now I'm going to take away the right-hand column, or I'm going to take away one of these columns and put drying and swelling next to each other. So now this is swelling, this is drying. So it's complicated and is not at all the same as the swelling process. And the reason, one reason, is that now the outer layer loses its water first, which means the outer layer is trying to shrink on top of a core that's soft and full of water. And in order to continue shrinking, you have to squeeze water through that outer layer that's on the outside. And so this leads to a very different dynamics than what you see during the swelling process. So obviously I'm not going to get into that in great detail right now. And the reason that I'm not going to show you a comparison of the model with the drying, so we can do this, but the problem is that the drying rate is actually very strongly controlled by what's happening in the room where you're drying the sphere. Because obviously, ideally, the sphere will give off water at whatever rate it likes based on the chemical potential. But you have to then remove that water from the sphere. And that happens by evaporation. And evaporation doesn't necessarily happen as fast as the sphere wants it to. And so as a result, you have to choose what the evaporation rate is, which is just the maximum rate at which water can be taken away from the sphere. And as a function of what you choose, you get very different results for the drying process. So on the upper left-hand plot, I'm not going to talk about the other ones, but the upper left-hand plot is showing you the radius as a function of time for different evaporation fluxes. And what we see is that you get this linear regime, which is basically the slope is exactly the evaporation flux because it's swelling as quickly as it can based on this limit.
Are you assuming drying happens isothermally?
Yes. Yeah, so we're not doing any of the complicated aspects of drying. We're just assuming that evaporation from the sphere is happening at any rate it wants up to a maximum, and it can't go faster than that, whatever that rate is. So the results I showed you a moment ago, so these plots are for free drying, which means it can lose water as fast as it wants. But in fact, constrained drying is a little bit different. Okay, and I'm going to stop.
Questions?
Did you try to put these gels into other liquids?
So no is the short answer, but you can, for example, put them into water with a solute, so salt water, and they will behave, I guess, more or less the same, but the salt does change say, the equilibrium size. And then if you wanted to model that, you would really have to deal with understanding how much salt goes into the gel versus how much will stay outside, and it becomes a lot more complicated. So yeah, glycerin's a funny case. I have put one of the gels into glycerin and basically nothing happened. And so glycerin is tricky because it also is very hygroscopic. So it really wants to suck up any water that's available. So it's not really clear how the gel and the glycerin interact with each other in that situation. Additionally, glycerin is much more viscous, which means that a process so 1,000 times more viscous for pure glycerin versus pure water, which means that a process that takes a few hours with water is going to take a very long time with glycerin. So, but I have done it with water-glycerin mixtures, and then it swells fine. The equilibrium size is a bit different, but.
Rich, go ahead.
I guess when it's drying and it's drying from the outside, you have a dry layer and a core which is wet. So
yes.
I would imagine there's tension
yes.
in this dry layer.
Absolutely.
Can you ever visualize any evidence of the tension? Is it very strong?
So so one thing I didn't talk about is that, let's see if I can say this succinctly. So swelling is a scale-free process. So precisely because when you make the equations dimensionless, there are no parameters that control anything except the final size. That means that if you take a sphere that's twice as big, you're going to see exactly the same process, just twice as big, and it will take longer or shorter.
Do you get patterns or anything, or cracking or anything?
So for large spheres, you get all the same patterns that you get for small spheres, precisely because of this. For drying, free drying is also scale-free. So you'll see all the same stresses, for example, during the drying of a big sphere as you do during the drying of a small sphere. But evaporation-limited drying is not. And that's because when you introduce the evaporation flux, there's now one dimensionless parameter. And so you can imagine that if you dried very, very slowly, so you had a very strong limit on the drying rate, then basically the moisture content in the sphere would be homogeneous and it would just shrink. Whereas if you dry very fast, then you get sort of the maximum non-homogeneity in the water distribution. And so
Free drying the fastest you can.
yes, exactly. So free drying is the fastest. And so when you look at this dimensionless parameter for drying, what we see is that effectively large spheres are closer to free drying than small spheres. And so as a result, it's not at all surprising, or it shouldn't be unexpected, that large spheres will have a much larger tensile stress on the outside. And in fact, when I bought a whole bunch of these spheres initially, so they come in a wide variety of sizes, down from dry sizes down from less than a millimeter up to a couple centimeters. And the ones that are a couple centimeters swell to a size that's, I'd say 10 centimeters or something like that. And I don't have any of those left because they all cracked when I was drying them. So it absolutely does develop a large tensile stress on the outside. And if you exceed a threshold, then they start to break.
The big ones sort of slump under gravity, or do they just?
They do a little bit, yeah.
Like jellyfish. Okay. More questions? Yeah.
This might be a foolish question that was resolved years ago in the Flory-Huggins polymer model, but I noticed in the drying movie, you start off with a meniscus of water around the base of the sphere between it and the table, and then as it shrinks, that disappears. And I was wondering if there is a validation of the model in testing when it becomes energetically unfavorable to have free water in contact with the sphere.
Yeah, that's actually a great question. So in principle, that's something the model should be able to do. So you should be able to have, if you had a 3D model, you should be able to have a region of the sphere that's exposed to air and a region that's in water. And then you take water out of this reservoir as you like. But in a spherically symmetric model, obviously this is not something that you can do. So we haven't done the 3D version yet. We're actually working with a guy who knows a lot more about sort of 3D finite element simulations than we do to try to do the 3D problem. But it's pretty tricky for swelling especially. For drying, that's actually a very good suggestion, so to try to model that problem. I was a bit surprised, to be honest, because as you said, there's this little meniscus of water at the bottom, and it does disappear before the sphere is fully dry, but I fully expected that meniscus would go away first. So the meniscus would evaporate, and then the sphere would start to dry, because I thought the sphere would prefer to steal water from the meniscus rather than to give up the water that it has internally. But it turns out that's not what happened, which I'm sure, again, the model will have something to say about.
Do this.
Sorry.
As you said, when it is swelling halfway, it's not spherical anymore.
Yes.
Did you do the experiment, or if not, what do you think will happen? You take it out before it has reached final. Would it redistribute, become spherical outside water?
So that's a great question, and yeah, that's exactly what happens. So if you swell it halfway, the moisture content is then non-homogeneous, which is what leads to the pattern formation. If you then take it out of water and stop the swelling process, then over time the moisture content will redistribute, and you'll end up with a sphere that's partially swollen. Yeah, exactly.
Well, go ahead. If you do this in plane geometry for drying, can you do a better job simulating the geometry of mud cracks than just stretching of a uniform elastoplastic sheet?
Ooh, that's a good question. I guess I don't know enough about the model that people use for drying mud cracks to claim that we could do a better job. But maybe? Rich, do you know anything about this?
I'm just wondering, which are you drying from the radial edge or from the surface?
Put it in plane geometry. Take a flat layer of mud and dry it from the top.
You'd have to have a different initial
Then there's
condition.
no tension. That's flat. It's half space.
Pretty well surrounded.
It reminds me of what's happening with
I mean, the physics are roughly the same. So gels are a nicer system for studying swelling than things like clays, because clays are sort of multi-scale porous media. So the clay grains themselves actually soak up water, and then the pore space between the clay grains soaks up water. So models for swelling clays tend to be a lot more complicated than what I just showed you. Gels are nice and homogeneous, and it's just polymer molecules and water. So it makes your life a little bit easier in that regard. But it would be interesting to play with that.
But how would you keep it plain? I can imagine you'd start it plain.
Well, mud cracks don't stay in the plane, right?
Sorry?
Mud cracks don't stay planar, they bend up at the
Well,
edges.
I don't think this would either. It would start to swell a little bit and it would go into preferentially a spherical shape, maybe, or go towards that.
Also, you can get mud cracks in sandy soil, you don't need clay. So.
Yeah, that's a good point. Yeah, you could do it with just very small particles. Yeah.
You have a question?
No, I just would comment that for big radius, it's almost like a plate. So if you look for a huge R extension, maybe your model can interpret this.
That's interesting. I mean, in principle, the model that I presented before I simplified to spherical symmetry is fully 3D. So in principle, we should be able to do the planar problem. We just haven't looked at it. Yeah, some of the, so if I go back to my little collection of pictures, so the one at the top is a planar layer of gel in a petri dish, but this is just the swelling problem. So they didn't do drying, and they also didn't let it get to its final state, at least in these snapshots. It didn't know, I mean, you can see, yeah. It was a planar layer of gel, yeah. And it will be again, probably, but in the middle it's not.
The only reason for doing planar things or two-dimensional things is they stay planar or two-dimensional.
Yeah, yeah.
If you start with something two-dimensional, it goes to be three-dimensional.
Well, unless that's the problem you're interested in, I guess.
Oh, it doesn't make it easy.
True.
Hey, Mark, did you have one more?
I had some sort of experimental questions. So for the drying, of course, the fact is that it sits on a table and it has this sort of wetting annulus around it.
Yeah.
Is it possible for small enough beads to sort of suspend them in an airstream, which would, like, have you ever tried that with like a ping pong ball and a hair dryer? I was wondering whether that'd be a way to suspend it so it doesn't touch anything, plus you remove all the moisture.
Yeah, that's a cute idea.
Polymers on the former space shuttle.
Yeah, I mean, I guess in principle it should be possible, right? You can do it with a ping pong ball, but I think a gel sphere that's the equivalent, you'd have to do the high Reynolds number math on whether you can actually suspend a sphere with an airstream, right? Because you need it to be big enough but light enough, and these have the density of water, so I'm not sure that you could do it.
Density will change over time.
The density will change over time. That's true. They'll get lighter.
Of the bulk density.
Or actually, I don't. Yeah, they'll get heavier. In fact, because the polymer is slightly dense relative to water.
One more question, then we need to go to lunch.
Maybe interesting to know that similar experiment has been done with a block of gel, much larger, and it was rectangular or cubic to start with. And during the process, it changed shape completely, developed legs, stood upright, and at the end became a block again.
Yeah.
I thought you were going to say it walked away.
No, started talking.
That sounds like a nightmare to model, but
Let's thank our speaker and go get some food.